Let me tell you about a specific failure I kept hitting when evaluating vector databases for a production AI system. I was running semantic search over a product catalog. A user searched for iPhone 15 Pro Max 256GB. The system returned the 128GB variant at 99.2% similarity. That is not a relevance problem. That is a correctness problem. The 128GB and 256GB are semantically almost identical. Same product line, same materials, same form factor. The only thing that matters to the user is the storage size. And it is the one thing semantic search cannot distinguish. This is not an edge case. This is a fundamental architectural limitation of pure vector search, and it shows up the moment your data contains precise identifiers. Model numbers, CQs, version strings, proper nouns, technical specifications. The episode is about why that happens at the architectural level. And now hybrid search combining BM25 sparse vectors with dense semantic vectors solves this. No code in this episode. We are doing architecture and benchmarks. If you came here to see Qdrant Python code, that is episode 2. But if you ship the code without understanding this, you will build wrong system. This is episode 1 of Qdrant Hybrid Search Engineering. Let us get into it. Start with the people who use search, because the problem is not about algorithms. It is about who is searching it. Any production search system serves two fundamentally different types of users, and they want opposite things. On one end is what I call the expect searcher. This person treats the search bar like a command line. They type like iPhone 15 Pro Max 256GB and expect exactly that. Not something similar, not something close, exactly that. These are power users, procurement teams. Engineering look up a specification. The query is a precise instruction. On the other hand is the casual user. This person types high-end Apple phone with a lot of storage, similar to this. They do not know the exact model name. They are describing intent, not issuing a command. For this user, semantic search is perfect. It is understanding what they mean even if the words do not match any document exactly. Here's the problem. A single retrieval method serves one end of the spectrum well and fails the other. BM25, the classic keyword algorithm, gives the expert exactly what they want. iPhone 15 Pro Max 256GB matches only documents containing those exact tokens. But ask BM25 about a device to go up floors and it returns nothing, because it does not know that lift and elevator are the same concept. Pure semantic search gives the casual user exactly what they want, but ask it for iPhone 15 Pro Max 256GB and it returns 128GB variant because it's embedding space. The two products are 99 the same. Hybrid search is the architectural answer. Run both retrieval methods and fuse the results. One system, both ends of the spectrum. Let me show you exactly what those failures look like in mechanistic detail, not just as an analogy. Here's what the exact failure mode is. You have a product catalog. You have dense embeddings of every product. A user searches for iPhone 15 Pro Max 256GB. Your embedding model, for example, let us say all mini LM L6 V2, something like that, encodes both the 128 and 256GB variants into the same 384 dimensional space. Both are iPhones, both are Pro Max, both share every token except one, 128 versus 256. In the semantic space, their cosine similarity is 98%. They are nearly indistinguishable. The search returns 128GB variant at rank 1 because it happens at appear first, or because of some other latent waiting, and the user gets the wrong product. In a real system, this means a wrong piece code, a wrong inventory check, a wrong recommendation. The deeper problem, semantic models deliberately smooth over surface differences to capture meaning. The 128 versus 256 distinction is exactly the kind of surface difference they smooth over. This is a feature of dense embeddings, not a bug, but it is a problem for exact lookups. Dense search is the wrong tool for queries the exact tokens matter. Sparse search is the right tool, but we cannot just switch. We need them both. Now the mirror failure. What happens when BM25 faces an intent-based query? BM25 fails in the opposite direction. It is a token matching algorithm. It compares the words your query to the word in each document. If a word appears, it scores. If it does not appear, the document is invisible. Classic example. For example, you have a building maintenance knowledge base. A user searches for lift maintenance schedule. But every document in your database uses the word elevator because the system was written by American engineers. BM25 returns zero result. The documents exist. The information is there. The user just used a different word. This is the vocabulary mismatch problem. It is not solved by adding synonyms to the query. That is a patch that breaks as soon as you hit a domain with enough jargon. Medical systems, legal systems, engineering documentation, everywhere there is domain-specific language, BM25 breaks for users who do not know the domain vocabulary. Dense search handles this perfectly. Lift and elevator live close to each other in the embedding space because they appear in similar contexts across millions of training documents. The semantic model already learned the synonym relationship, so you need both. Dense search for intent and concept matching, sparse search for exact token precision. The question is how to combine them. Before we get to the fusion strategies, let me show you exactly how each method works internally, because understanding the mechanics is what lets you tune the system. BM25 means best matching 25, has been a gold standard for keyword retrieval since 1994. Here is how it scores a document against a query. First term, frequency. If a query terms appear in a document, that is a signal, but BM25 applies saturation, controlled by the key 1 parameter. The intuition, appearing 10 times is better than appearing once, but appearing 100 times is not 10 times better than appearing 10 times. There are diminishing returns. In practice, this prevents long documents from dominating just because they repeat words more. Second, inverse document frequency. This is the rarity filter. A word appears 90% of your documents, tells you amongst almost nothing about relevance. Words like the, and, is. A word that appears in 1% of your documents is highly discriminative. BM25 weights terms by how rare they are across the collection. Common words get penalized. Rare, precise terms get rewarded. This is why gorgonzola in a query cuts through no is far better than cheese. Third, document length normalization. Longer documents have more words, so they have more chances to contain any given term. BM25 normalizes score against the average document length in the collection, controlled by the B parameter. This prevents long documents from outranking short, highly relevant documents just by virtue of their length. In Qdrant, sparse vectors represents BM25 scores as high-dimensional vectors, typically 30,000 plus dimensions matching a vocabulary, but mostly zeros. The only dimensions corresponding to the terms that actually appear in the document have non-zero values. That sparsity is what makes the computation fast even at 30,000 dimensions. Now the other layer, dense vectors and how Qdrant navigates billions of them in under 10 milliseconds. Dense vectors encode meaning as point in high-dimensional space. A 384-dimensional vector from all mini LM-L6V2 or a 1536-dimensional vector from text embedded 3 large, every dimension is non-zero, representing some learned semantic property of the text. The mental model that works best. Think of embedding space as a geometric landscape. Every piece of text has coordinate. Texts, that means similar things clustered together. Apple is closer to the peer in the fruit region of that space, and close to iPhone in the technology region. These are different dimensions literally. Finding nearest neighbor to a query vector is that landscape is the problem. With a million documents and 384-dimensional vectors, brute force comparison is too slow. Qdrant uses HNSW, hierarchical navigable small word, a graph structure that lets the search algorithm jump to approximate neighbor of the query very quickly. then traverse precisely within that neighbor. HNSW achieves sub 10 milliseconds P95 latency at 1 million vectors. That is what makes real-time rack systems possible. But there is a subtle failure mode specific to Qdrant's HNSW that is worth understanding: disconnected graph problem. If you apply strict post filter, say only return results in category X after the ENN search, you might find that the nearest neighbor in the graph all failed the filter. The search terminates without result even though relevant documents exist. Qdrant solves this with in-graph filtering. The filter conditions are embedded directly into the HNSW graph traversal. The algorithm only navigates to nodes that satisfy the filter. This guarantees valid top key results and is one of the key architectural advantages Qdrant has over simpler HNSW implementations. Now we have both methods, BM25 sparse and dense semantic. The problem, their scores are not comparable. Here's why, and how Qdrant fixes it. The naive approach combining BM25 and dense search, run both, add the scores, re-rank, do not do this. Here's why. BM25 scores are unbounded. A highly relevant document might score 14. A moderately relevant one might score 3. The range depends on the document length, the vocabulary, the collection size. You cannot predict it. Cosine similarity scores are bounded between 0 and 1. A very relevant document scores 0.97. A moderately relevant scores 0.83. If you add this directly, the BM25 score of 14 swamps, the cosine score of 0.97. BM25 dominates the fusion completely, regardless of what dense search found. You have not combined two signals. You have to run one away. You need a normalization step. And two approaches Qdrant supports different trades-off that are worth understanding before pick one. First, Reciprocal Rank Fusion. The default, and for most cases the right choice. Reciprocal Rank Fusion, RRF, solves the scoring problem by ignoring the raw scores entirely. It uses rank positions. Here is the formula. For each document, its RRF score is 1 divided by key plus its rank position, summed across all retrieval lists. Qdrant default key is 2. The research literature uses 60, but Qdrant deliberately chooses 2. A smaller key amplifies the importance of top-ranked documents, rewarding strong consensus between two retrieval methods. Let me walk through a concrete example. Say the dense search ranks document 1 first, and document 3 third. The sparse search ranks document 5 first, and document 1 third. Document 1's RRF score is 1 divided by 2 plus 1, plus 1 divided by 2 plus 3. That is 0.93 plus 0.20. Total 0.53. Document 5 only appears in one list, so it scores only 0.33. Document 1 wins because it's ranked in high in both. This is the key insight of RRF. Consensus beats dominance. A document that ranks second in both retrieval methods beats a document that ranks first in one and appears nowhere in the other. The system rewards documents that are relevant across multiple retrieval signals. RRF has no hyperparameters to tune beyond key, which Qdrant sets for you. It is robust to outlier scores. It is the right default for general-purpose hybrid search. The alternative is DBSF, when you want score magnitude to matter, not just rank positions. Distributed Base Score Fusion, DBSF, takes a different approach. Instead of ignoring the raw scores, it normalizes them so they become comparable. The normalization is the 3 sigma rule. For each retrieval list, compute the mean score and the standard deviation. A score is normalized as score minus mean divided by 3 times the standard deviation. This maps most scores into a bounded range of roughly -1 to +1, with outliers clipped at the extremes. After normalization, you can add the scores from the both lists. Because they are now the same scale, magnitude of the score is preserved. A document that scores 3 standard deviations above the mean in the dense list generally more relevant, and the DBSF reflects that. When do you want DBSF over RRF. In e-commerce, when the search engine's confidence score matters, when a 99% match should outrank the 95% match by more than just rank position. For catalog search, where you have strong relevance signals, DBSF often gives the sharper rankings at the top. For everything else, question answering, document retrieval, general RAG, RRF is more robust and you should use it. Now the payoff. What does this actually deliver in production? Here are the benchmark numbers. Here are the numbers I found when evaluating production vector databases. There are 1 million vectors, a realistic production scale. Qdrant self-hosted 850 to 1840 queries per second, 8 millisecond P95 latency. Pinecone serverless 340 to 500 QPS, 28 milliseconds P95. pgvector with HNSW 220 to 360 QPS, 48 milliseconds P95. VV8 Cloud around 380 QPS, 18 milliseconds P95. For most teams starting with RAG, pgvectors is natural choice. It's already in your Postgres. It is perfectly adequate up to few hundred thousands vectors. The moment you push past 2 to 5 million vectors, the P95 latency starts climbing rapidly and the QPS drops. The architecture does not scale linearly. Qdrant is written in Rust with HNSW and segment-based storage system designed from the ground up for vectors operation. The 8 millisecond P95 is not marketing. It holds under real concurrency base. Qdrant handles asynchronous segment merges and index construction without blocking the query path. The hybrid search story adds precision on top of this performance. You are not trading throughput for accuracy. You are getting both. That is the production argument for the Qdrant. The 13% precision improvement claim you see Qdrant's documentation is reproducible. In episode 2, I will show you side by side on 500 real products records the same query, dense only versus hybrid, with concrete precision numbers. Let me bring this together before we move to the code in episode 2. Here's what we covered. Production search system serves two types of users. Expert searchers who need lexical precision and casual users who need semantic understanding. BM25 serves one, dense vector serves the other. Hybrid search serves both. The two failure modes are concrete and predictable. Semantic search fails on exact identifiers, model numbers, SQs, version strings. Because the embedding model deliberately smooths over the surface differences, BM25 fails on intent queries because vocabulary mismatch leaves the search engine blind. Fusion requires normalization. You cannot add BM25 and cosine scores directly. RRF is the robust default. Rank-based, consensus-driven, no turning required. DBSF is alternative when score magnitude carries the meaning. Qdrant's HNSW with in-graph filtering solves the disconnected graph problem and delivers 8 millisecond P95 at 1 million vectors. The performance foundation that makes a production hybrid pipeline viable. In episode 2, we build it. Collection setup with named dense and sparse vectors. Fast embedded for BM25. No Elasticsearch dependency. The prefetch API running both searches in a single request. And the side-by-side comparison that puts a number on the improvement. If you found this successful, please like and subscribe. The GitHub repo is Qdrant Hybrid Research Lab. Branch episode 1 concepts has architecture diagrams and benchmark data. Links is in the below description. Thank you guys.